share.
Yes, you can see
Yeah.
your screen now.
Okay, cool. Let's do this, man. Hello, everyone. Thanks for joining us. My name is Andrey. I'm a developer at TransFICC. And today I'm going to talk a little bit about a stub service we built for one of our clients to help with when we were testing, and how we went about designing this and profiling this and some lessons we learned from this. So as a bit of a background, TransFICC is a software vendor and financial services. Our core product is unified API for fixed income trading venues. So we kind of provide the canonical protocol to send orders, receive prices, do requests for quotes, and all the other evil financial things. And you integrate with once, and we translate that canonical protocol into the native protocol of a particular venue, and we also handle some of the kind of behavioral quirks of some of those venues. So we publish the protocol to our clients, and it's a binary protocol using simple binary encoding for serialization. So for those who don't know, it's a very efficient serialization mechanism. It's a kind of open standard. You can Google it. But it's a little bit fiddly to work with, and there are other things like maintaining connection and that sort of thing. So as a convenience, we also offer Java and C# libraries, which are very thin layers on top of the SB codecs. And also, since it's a binary protocol and there's kind of less tooling around that, we provide people a stub service, mostly for end-to-end testing. So the idea is pretty simple. You start up a TransFICC stub. You start up your application with our library in it. Library connects to the stub, and then you can actually drive the behavior from tests, like throw messages into the system or a certain things sent by your code by the system under test. And recently, one of our clients wanted to do a slightly different kind of test. We wanted to do more of a performance/capacity test, but again, end-to-end. Tried the stub, quickly realized it's a bottleneck, kind of unsurprisingly, because it was initially designed for low volume BDD style tests, not any sort of benchmarking. So we set out to redesign stub and make it useful for both functional and non-functional testing. And the design we come up with, based on sort of collective experience in the team, was a fairly typical NIO loop. So you have a single thread running in a tight loop. We're actually using Agrona agents. Those who are not familiar, it's a threading pattern borrowed from gaming and kind of real-time systems, where you run this tight loop, and in every iteration you're doing a little bit of work. It needs to be lightweight and time-bounded, and then you just run as fast as you can. And if you run out of work to do, you can back off, or you can do something else. And Agrona provides a very nice abstraction of that pattern. So we run this IO loop, kind of read data from the socket, decode it, hand it to some pluggable behavior, and if behavior, this business logic needs to send data back, again, we encode it and write to the socket. So very classic IO system, single-threaded, which has some interesting implications for performance I'm going to talk about later. And once we had this new design kind of tested and knew it's working, naturally we wanted to profile it and see if it can actually meet the demand. And I think the ask was to do something like 20,000+ messages a second, which is for non-blocking IO system with a good serialization is actually not that much, and we were confident we could handle this, but nevertheless, let's profile. So the benchmark setup is, again, pretty simple. We have one process hosting the stub. We have another process which has our library in it and the actual benchmark. And they talk over TCP loopback because we're interested in what the code is doing, not network bandwidth. So the benchmark generates number of messages on every cycle, let's say 5. Pushes them through the library to the stub. Stub simply acknowledges every message. And benchmark records those results and calculates the average throughput over time. And it's a bit of a crude measure, but it's still useful. It gives you an idea of what system is capable of. But also, if you're going to make any changes, it's going to highlight, sort of show you whether you're making things better or worse. And yeah, this was basically a description of the next slide. So we ran this benchmark, and it came out initially at about 30,000, which kind of fits the bill, but just about. Now, immediately we know there are a couple of things which are suboptimal and we could improve. So first of all, our cycle looks like this. Read from the socket. We're doing non-blocking read, so we're reading as much bytes as we can. But when we only dispatch a single message to our pluggable handler, and when handler sends the response back, we're really writing this to socket in line. So first obvious thing to improve is to dispatch more than one message per cycle, up to some limit. So we already made an expensive call to the socket to read the data. Let's kind of make good use of this data. So this is essentially what Java buffered input stream is doing, right? Similar kind of pattern. So we implement this, throughput goes from 30K to 150. Okay, like that's a nice improvement. Now, second obvious thing is, say we dispatching 10 messages and send 10 responses back. But we're still writing every of those responses to socket one at a time. So the natural thing is, again, to just buffer them and then flush this buffer at the end of a cycle. Very much what Java buffered output stream is doing. And we implement this, throughput goes from 150 to roughly 250. And obviously, we're running all the experiments on the same machine. So at this point, we kind of know we're exceeding the customer requirements by about a factor of 10, give or take. And agile kind of lean thinking school of thought tells you, stop right here, you've done enough, move on to the next thing. But it was kind of end of last year around Christmas, there was not a lot going on in terms of work because of holiday season. There was not a lot going on otherwise because of, well, COVID and lockdown. So I decided to take this as an opportunity to experiment and profile this thing a bit further and see if there is anything I can kind of improve and learn in the process. And initially, I was actually interested in profiling our library because we knew at this time that we can handle decent volumes. It works very well in production, but we didn't really know the limitations. So I ran this setup through Profiler, and this picture came up. For those who don't know, this is a tool called Async Profiler for JVM. It's absolutely awesome. It gives you a view of your code, like JVM native code operating system. It profiles the whole stack and gives you those really cool flame graph visualizations, which are also interactive. Well, you can see here, it's very interactive, unfortunately. But the interesting thing about this is that most of the time seem to be spent in a JVM method called JByte disjoint array copy. And you can tell it's JVM method because it's in red, it's kind of color coded. And this has happened when we're sending the message to the library. So what's going on here? Well, to understand that, I need to explain a little bit what's sending, kind of how our messaging works internally. So let's say we want to write something to the library. We encode those messages into bytes. We put them into byte buffer. We do in socket write. The write is non-blocking, so it won't flush the whole buffer. It can write just a tiny bit of it. And after that, whatever is left, we move to the any bytes left are moved to the start. We compact the buffer. This is a kind of classic NIO recipe. You can find it in tutorials and Java docs and things like that. So, and the reason for compaction is, of course, so we can have space in the end to write more messages later. And turns out that that compaction can be expensive. We're moving quite a few bytes, and it takes some time. In actual fact, it takes more time than any other useful work done in this process by like considerable margin. So we're basically just moving bytes. And also this compaction happens on every call and every message sent. So my first idea here is like, okay, we just implemented a sort of buffered writes in this tab. Maybe we can try the same in our library. So let's not write all the data to the socket. Let's only put into byte buffer, do a single write, and hopefully this will reduce the cost of compaction and improve the throughput. Well, I tweak the library on a branch, run the experiment with changes library, and well, it didn't really work. The actual throughput, by the way, is about the same. So it's still 250-ish. But now this compaction is absolutely dominating the profile. So it's clearly a bottleneck. So, OK, first idea didn't work out. Let's go back to the drawing board. So why compaction is expensive? Well, it's because it must be moving lots of bytes. So what does it mean? It means that our buffer is probably mostly full. So why IO buffer is mostly full when we're writing data? Well, maybe the other end is not keeping up. So let's profile this tab and, oh, hello. We have similar kind of problem. Again, JBudget's joint array copy is a significant cost. But now it happens when this tab reads the data from the socket. And the mechanics are very similar. Because again, the way read works, it fills the buffer from TCP stream, it dispatches messages to the handler, and then compacts any leftovers. So now I understand the problem. I can kind of try to introduce some tunables, play with buffer sizes, number of messages, etc. But this is a little kind of, it doesn't feel quite right because those values would have to be configured for a particular workload and what are even sensible defaults. So is there a way to eliminate compaction altogether and make this thing a bit smarter and robust? Well, there is a classic approach to those sort of problems, a ring buffer. The idea is quite straightforward. Instead of moving bytes, you maintain 2 pointers, and you just move those pointers sort of around the buffer. And in this case, for example, when reading data, we're going to fill the buffer right at the end, until the end. And then few other bytes which are available in the socket will go actually at the start. And when we dispatch, we move head forward. Now, it's all very nice. There is a little bit of complexity involved. So this is TCP stream, not any messaging system, really. So it's just a stream of bytes, which means that individual message could be fragmented. So you can have 100 bytes sitting at the end of a physical buffer and all the other bytes sitting actually before that at the start. Also, our messages have a little header, which is just 4-byte integer which tells you how long the message is. And this is to help delineate TCP stream and split it into individual messages. That header itself could be fragmented. You can have 2 bytes at the end, 2 bytes at the start. So kind of need to write a little bit of code to handle all those cases. But it's not too difficult. It's fairly straightforward, fairly easy to unit test. So let's try that and see if it makes any difference. Does the complexity pays off? Well, it does. We go from 250 to about 800K. It's like, OK, that's a nice improvement. Have a look at Profiler. Stub is mostly doing something useful, which is nice. The other end library and the benchmark also doing something mostly useful. No obvious waste here. Nice. So, OK, can we now we have kind of established that this is an improvement. Let's try to push the system in different directions and see if there are any other interesting cases. So, for example, we're writing 5 messages per cycle in the benchmark, but handle 10 in the stub. So we're probably not saturating consumer. Well, our reader is now really efficient. Let's push 10 messages and see what difference does it make. Hopefully this will improve things, and we're going to use available bandwidth even better. No, not really. Instead of any improvements, we get more than 2 times drop in throughput. Now what to do? Back to profiler. Stub is still looking good. Library, well, you can guess, compact in memory, now in the read path. And it's exactly the same problem because obviously the code is quite similar and sort of followed the same patterns. It's like how it was historically. Okay, so we have a read buffer in the stub. We can try the same in the library. And I jump on another branch, make a little tweak, put a read buffer in, rerun the benchmark, and yeah, now we can cross 1 million messages per second mark. And this is just a little Metallica reference to lighten the mood. So, however, it's not all plain sailing. We're running 1 million messages a second, but now it's a bit flaky. Every now and then we get like a genuine TCP back pressure. And turns out Stamp doesn't handle it very well. It kind of throws errors, drops connections, it disrupts the benchmark. So, okay, we can improve on that. Do a little tweak to put some more sensible, more intelligent sort of back pressure handling. Rerun the benchmark, still no lag. But now it misbehaves in a very peculiar way. After kind of few tens of seconds, it sort of stalls and pauses for 10 seconds and nothing's going on apparently. And then stop disconnects the library because it thinks that remote end has gone away because no messages has been received. And my initial thought is that, okay, maybe I screwed up my back pressure handling and somehow I'm stalling one of the threads for long enough for this to happen. And I'm sort of trying to debug this problem for a long time and trying all sort of things. It's like, let's add some diagnostic to see how long the cycle takes. And it tells me, no, actually, everything is running pretty smooth and there are no long cycles. It's like, okay, maybe there's some quirk in the TCP stack. I'm trying to Google for TCP tuning suggestions, and that's like a rabbit hole. No, I'm not prepared to do this. So finally, I stumble at the kernel stats, and you can actually look at the state of the kernel socket buffers in the kernel. And the following picture emerges. Both threads, my benchmark and my stub, running as fast as we can, don't stop. Socket buffers on both ends are kind of full, so there are some data there, and we're pretty close to the actual buffer limitations. And in which case, the fact which the stub doesn't read anything for 10 seconds kind of doesn't make sense. So maybe it's not a performance problem after all. Maybe there's something more mundane. Let's debug it, and wow, we have a bug. It's a bit of an edge case, but it's fairly simple integer overflow problem. So if you remember those 2 pointers, head and tail, they kind of meant to be used as unsigned integers. So obviously Java doesn't have a native unsigned integer type, but you can kind of simulate this. You can apply bit masks or subtract those numbers, and this gives you some meaningful results. What you cannot do is directly compare them. And the code did exactly this. And once at a higher volumes, one of the kind of pointers overflow into negative value, it's broken. Fairly easy problem to reproduce in the unit test, fairly easy problem to fix, rerun the benchmark. Yeah, now it's stable. We're actually doing a little more, about 1.1 million, because some along the way, I fixed one of the minor problems related to compaction as well. Well, again, based on previous experience, let's try to push this thing in different directions. Let's try to saturate the consumer. Let's try to write more than messages per cycle in the benchmark. Then the stub handles, still stable. Let's kind of experiment with various ratios. It's all looking good. Everything is stable. The throughput actually improves at some point because we're probably making more use of a bandwidth. And profiler looks good, so no easy wins here. And I'm thinking, yeah, that's probably the best we can do. And 1 million, just over 1 million sounds like a nice number, so maybe that's enough. And then kind of just casually, I glance over benchmark and I noticed something interesting. So the benchmark is single threaded, but it runs both load generator and the library in the same thread. And it tries to offer, say, 20 messages. Now, our library is done blocking, so when you trying to write a message, it actually gives you a result whether or not it has been written or not. And if you cannot write because there's no space in the buffer, it tells you you've been back pressured. And at which point you'll have to wait a little bit and run the library cycle to unblock the loop and the system as a whole. But the benchmark doesn't do this, it blindly tries to offer 20 messages. So, which means that library cycle is not executed for a little bit, and we're kind of wasting some CPU cycles. So what happens if we break early? What happens if we'll try to write up to 20 messages, but if we cannot, we'll sort of go back to doing library work? What happens then? And it turns out we can do about 50% more in this setup. And it's nothing to do with the actual production code. It's to do with the way test harness is set up and benchmarking methodology. And the benchmark itself was actually a limiting factor in this case. And I promise this is the last Metallica reference. So it turns out we kind of sends just under 10 messages typically. And I've tried to run a few more experiments with different buffer sizes and number of messages. And it's kind of floats at around 1.7 million. This is probably the limitation of this particular benchmarking methodology. So to push further, I would have to write completely different, to set up completely different experiment with multiple threads. And I didn't have time to do that really. But one thing I had time to do is to resurrect inline write the library, see what's going there. Unsurprisingly, we go from 1,700 to about 900,000. Kind of expected we're making more system calls, we're spending more CPU cycles doing sort of other work, not useless work, but the expensive work. Still, it's kind of a nice improvement from initial 250. So, as I mentioned, the whole exercise was largely about kind of learning and experimenting. And what did I learn from this? I think, for me personally, the most surprising thing was that overflow problem. It took me insanely long time to figure this out, but not because the problem was hard, but because I was so convinced it's something to do with performance and kind of the stress the system is under, which I didn't even think it was a functional problem. And only when I sort of took a step back and tried to move in the kind of to poke it from a different angle, then it became apparent that no, it's not. And I was like completely blind to this normal functional defects side of things. So it also reminded me that those kind of stress tests is a good addition to normal unit tests, because just of a sheer volume of things which happen, it can pick up kind of rare or uncommon problems. The other things I was kind of reminded of there's this beautiful quote by Alan Key, one of the authors of object-oriented programming. You get simplicity by finding a slightly more sophisticated building block. And we always have this idea, again, kind of coming from agile thinking, do the simplest possible thing. But simplest possible thing is not the dumbest possible thing. And actual simplicity has a certain sophistication about this, kind of counterintuitively. And if you do just something naive and dumb, it becomes a limiting factor. And this is true for production code. This is true for performance experiment. This is true for your test as well, I think. And whenever you're doing any profiling work, obviously you need to pay attention to both the code on the test and the benchmark itself. Benchmark should add as little overhead as possible. Some trivia about I/O. So non-blocking I/O is non-blocking, which is nice, but it's still expensive. As kind of hopefully everyone knows, system calls are not free, but in relative terms, we can be cheap if we amortize that cost by doing more useful work per expensive operation. It's like Martin Thompson in his talks and presentations and articles talks about smart batching, and this is, I think, a good example. Batching things smartly is good for performance. And also, threading and I/O are interconnected. You cannot really think or design I/O model without thinking about threading, and the other way around. Sort of the way you assign responsibilities to threads is one of the big factors in performance of the system. So in our case, we opted for single threaded, which is really nice and simple and very easy to implement and test. And there's a lot of nice things about working in a single threaded environment. But it also means we're actually basically doing 2 or 3 different kinds of jobs in the same threads, reading from socket, writing from socket, executing actual code. And none of them could use that thread to the full, so they're competing with each other, and this becomes a limitation. And last but not least, I guess, not talk about performance would be complete without a rant about premature optimization is the root of all evil. And this quote from kuh-neh-vin is often used as an excuse for all sort of sloppiness and inefficiencies. But actually, in the original article where it appeared, it's a lot more complicated and subtle. He goes on for 2 or 3 paragraphs about do's and don'ts of optimization. And sort of my take on this currently is we should try to write efficient code in the same way as we're trying to write code which doesn't have functional defects, doesn't crash, doesn't surprise our users in some nasty ways. We should try to write code which is efficient and runs smoothly and can handle kind of decent volumes. What we shouldn't do is we shouldn't optimize based on a hunch or a gut feeling. We should use the best data we can get our hands on. Production metrics, that's probably the best available possible data. Benchmark, even your own kind of personal experience may count as data, although you obviously need to periodically revise it and sort of calibrate your mental models. And of course, any optimization should not break things in terms of functionality or maintainability of a code, or hinder other work which is important for your organization. And you should optimize system as a whole and really optimize for a micro goal. And this is what kuh-neh-vin is basically saying in the article. Don't get too obsessed with small inefficiencies. Look at the bigger picture and try to make the thing as a whole work nicely. And I think this is everything I wanted to talk about today. So if people have any questions, or I don't know how it works, is there a Q&A round, or they can write it afterwards. Thank you very much. I think you're on mute.
If people have questions, they can put in the chat or they can raise hand. I will unmute them. Or if you see them, the questions in the chat, you can answer directly. So I have maybe a question for you. Where is the advantage in comparison against Kafka?
So Kafka is a general purpose messaging system, right? And it's also kind of gives you replication and durability. So we just don't need replication and durability for our use case. So we're just doing a simple kind of socket transport.
Okay, thank you. There is another question in the chat. If you can see that, you can answer directly.
Yeah, so increasing throughput matters. I guess it mattered for me personally in this case, that's for sure, because I was approaching this as a learning exercise of sorts. But did it matter to our customers? I believe so as well. So maybe they would be happy with the initial 250K version. But it's always nice to have as much headroom as you can. And as a sort of, I did this as almost as a side project. But nobody asked us to do, a million messages per second. That was really, I was more in the mindset, let's try to make this thing do as much as I can, in a reasonable time.
I'm really sorry. I just realized that the question that I posted there, I managed to delete the middle line from it, so it probably didn't make very much sense. I meant to ask about latency. I meant to ask, did increasing effect on latency? And then I'm really sorry about that. That's a complete mistake by me. I'm really curious what happened to latency as you made those changes.
Yeah, so that makes a lot more sense, and that's a great question. Well, I didn't bother too much with latency, mostly because if you're familiar with coordinated emission, sort of problem in measuring latency, then the way our benchmark is set up is like prime example of coordinated emission. It wouldn't be very sensible. So intuitively, we eliminated some waste, so we probably improved the latency, certainly at the higher rates, but I didn't measure this systematically.
Well, thank you.
Where could be the business cases for, or use cases for business for?
So, as I mentioned in the beginning, the whole purpose of the stop is to enable automated testing by our clients. And it's kind of, initially it was all about functional testing, but also turned out people want to do those sort of performance capacity tests as well. And this is really to give them that option. So they want to test their own code, but in the end-to-end setup, without actually connecting to our service or like real Exchange, for example.
Okay. I am not. Chris, you want to say something?
So that was just me using the clapping hands emoji.
Okay. Yeah, thank you. Chris, you want to add something?
No, I just want to say thank you very much for that talk. That was really interesting. I'm actually doing some performance work on and off over the course of this year, so it's really relevant for me. There's some very, very interesting insights in there.
Ah, good.
Well, then, if there is not another question, we can close the session for today. Thank you all for joining.
Oh, wait a sec. Before we close the session for today, there is another talk.
Pardon. Yeah.
Yeah, no worries at all.
Sorry.
Oh, I thought I got away with it as well.
Okay, sorry.
I'll share my screen. Please bear with me whilst I do that. Yeah, like Barry said, things always go wrong, so I managed to delete half my question.
Yeah.
And now I don't know how to share the screen in Zoom. Let's try and figure this out. Share screen. So, can folks see my screen?
Yeah.
Excellent. So, in that case, I will begin. So, this talk, thank you very much. Thank you very much, Andrey, and thank you very much, Hassan, for running this. So this talk is called Making Sense of the Situation with kuh-neh-vin. And unlike the last talk, it is not a talk about hard tech. This is a talk about some of the situations we may encounter as software engineers and a framework, kuh-neh-vin, that helps us to make sense of them. So I work at a tech company, I beg your pardon, called Masabi. And this talk is partly inspired by some of the experiences I've had at Masabi and also in some previous roles. I'd like to start by telling a story. So once upon a time, many years ago, I and a couple of my colleagues performed a live release of one of our backend services. We deployed a new version of this particular backend service into our live environment. This was a pretty simple process. Even back then, we automated much of the process. Those parts that weren't automated were documented in a release ticket, a Jira ticket with a sequence of steps, a script, if you like, telling us how to release the service. So we simply followed the script and released the service. And having completed the release, we went to lunch. And unfortunately, our enjoyment of lunch didn't last long. We started getting alerts. The backend service that we just released was rejecting requests. Customers were being impacted. And so we rushed back to the office. When we got there, everything was on fire, metaphorically speaking, of course. So it turns out the situation was really bad. The release that we'd just done had caused some of the configuration of our service to be changed in a way we hadn't anticipated and didn't want, because this change was causing certain data belonging to that service to be corrupted. And the longer this problem goes on, the more data is going to be corrupted and the harder it will be to clean up afterwards. We weren't sure why the configuration of this service had been changed. We hadn't intended for it to be changed at all. We didn't have time to find out. We had to fix the service. We had to act quickly. So we manually switched back to the previous version of the config that had been live before the release. And thankfully, this put the fire out and allowed us time to work out how on earth we got in this situation and how we were going to clean up after it. The question is, what happened here? We thought we needed to just follow a script. And actually, we ended up needing to take rather drastic action to contain an emergency situation. Remember this story because we will talk about it again later on. Let's tell another story. So many years ago, in another previous role, I worked on a team tasked with creating a new software product. We'd received some feedback from our customers that an existing product that we had was really not meeting their needs. So we needed to create something better. This new product needed to solve our customers' problems, not the problems that we in the team thought they had, but the customers' actual problems. So we wanted to develop this new product in close collaboration with those customers using agile methods. So we wanted to work in monthly iterations, which was a big deal back then, continuously delivering working software every month, also a big deal back then, and getting feedback to allow us to change course if necessary. So maybe nowadays, this doesn't sound too controversial, but this was 15 plus years ago. Like I say, it was a big deal. And the trouble was the company for which I worked already had a process designed to ensure that we shipped software that met the requirements of our customers and of the market, and it looked rather different. So every product team in the company was required to follow this rather heavyweight process. And the process was designed, like I say, to ensure that we really did meet the needs of the market by thinking really hard up front, by committing to a year-long plan and being held to that plan. And each phase of the project, concept, plan, develop, and so on, was gated by a checkpoint. So, for example, the team couldn't start doing any development until we got past the plan checkpoint. In order to get past that checkpoint, the team had to write and submit a whole load of documentation and satisfy a committee that the plan really was okay, and then we'd be allowed to start writing code. Which kind of means you have to commit to a year's worth of features in advance before you're allowed to start coding. So let's be honest, this is kind of a waterfall process. How does that sound to everyone here? Does it sound like a good idea? Not to me, it doesn't. So this was a long time ago, and I don't blame the people who came up with the process, but you know what? Actually, we still managed to work in an agile way like we wanted to. We still shipped working software every month and got feedback every month. But our process made life hard for us. We had to pay lip service to this bureaucratic waterfall process, even though it was not how we were trying to work. So what happened here? The process told us to apply our expertise to analyze the situation up front and make a really good plan. But actually, we needed to proceed by trial and error, changing course in response to feedback. So this talk is about a framework that helps us to make sense of situations like this. It's called kuh-neh-vin, and it was created by this chap, Dave Snowden, many years ago when he worked for IBM Global Services. The name kuh-neh-vin, I'm told, comes from the Welsh language, hence the pronunciation, which might not be what you expect. It apparently approximately means habitat, a place where something resides and is at home. So kuh-neh-vin helps us to make sense of situations that we might face by giving us a set of domains in which a situation may reside. These domains are, in order of increasing complexity, obvious, complicated, complex, and chaotic. So let's start with obvious. In the obvious domain, which is also known as simple, there are rules in place that we can follow in order to deal with the situation. So if there's a process you can just follow without needing to think too hard about it, you're in the obvious domain. So an example would be if you phone up a call center and the person on the other end of the phone is obviously following a script. Perhaps they're operating in the obvious domain. Thinking about our work as software engineers, let's imagine we need to do some manual regression testing on a piece of software before we release it. Even in this day and age, we might still need to do that. So we may choose to write a test script that tells us exactly what steps to follow in order to test a particular piece of functionality. And if I can follow that test script by following that sequence of steps without needing too much expertise to do it, then I'm working in the obvious domain. In the obvious domain, cause and effect relationships are perceivable, predictable, and repeatable, and consequently, this is the domain of best practice. Kuh-neh-vin tells us to handle a situation in this domain, we need to sense, then categorize, then respond. Sense, observe the situation. Categorize, work out which process to follow, and then respond, follow the process. So, the question is, with reference to the stories that we started with, when were we in the obvious domain? Well, I'd argue that if we release our software by following a sequence of steps, or even if we automate the process, then we're in the obvious domain, or at least we hope we are. So that's the obvious domain, where we sense, categorize, and respond. The next domain we'll look at is the complicated domain. And it's complicated because it requires expertise. The complicated domain is the domain of engineers, surgeons, lawyers, and other experts. In the complicated domain, an expert can apply their expertise to analyze the situation and make and execute a plan to deal with it. One simple example of a problem in the complicated domain is servicing my car. Although I don't necessarily have the necessary expertise to service my car, There are folks at my local garage that do. They have the necessary expertise. Maybe an example of a complicated problem in our profession is implementing a very simple CRUD web app. It's relatively straightforward to do if you've done it before, if you've implemented an app like this before, if you know what you're doing, if you have the necessary expertise. So in the complicated domain, cause and effect is potentially knowable. The relationship between cause and effect requires analysis or expertise, and consequently it's the domain of good practice. And Cynefin tells us in the complicated domain, we can respond to the situation by sensing, analyzing, and responding. When we sense, we observe the situation. When we analyze, we use our expertise, and then we respond. So again, thinking back to the stories at the start, when were we in the complicated domain? I'd argue that this waterfall process treats the process of creating and releasing software as a problem in the complicated domain. Up front, we analyze the situation in order to make a plan, and then the assumption is we can execute the plan flawlessly. Okay, in theory at least. That's the complicated domain, where we sense, analyze, and respond. The complex domain next is different again. The complex domain covers situations where behavior is emergent. What do we mean by emergent? Well, sometimes there's no way to know how a system is going to behave, even for an expert, even with a lot of analysis, without performing an experiment, trying it out. Cause and effect in the complex domain can only be deduced in retrospect. And examples of complex systems include battlefields, ecosystems, markets. Looking at the slide, looking at the feedback loops in extreme programming or agile software development, the implication is that perhaps software development is also a problem in the complex domain. We mentioned markets. I would argue that companies, particularly startup companies, operate very much in the complex domain. Many years ago, the founders of Masabi, the company where I now work, they had a crazy idea that technology could make fare collection and ticketing better in public transport. But you can bet they didn't plan Masabi's next 10 years before they got started. They couldn't just think hard about the problem and use their expertise to plan it all out. Rather, they performed a number of safe-to-fail experiments. They released products, they got feedback, they changed course, they entered new markets, and so on. And each time, they were proceeding or changing course based on the results of those experiments. So I'd argue the company where I work lives in the complex domain, as do probably most companies. So in the complex domain, cause and effect relationships can be deduced, but only in retrospect, only by trying it. And consequently, this is the domain of emergent behavior or trial and error. And Cynefin tells us to probe, sense, respond in the complex domain. Probe, perform a safe-to-fail experiment. Sense, see what happens, and respond based on the feedback that we just got. So the question is, in the stories at the start, where do we think we were in the the complex domain? So I've already mentioned this really. I'd say making software in an agile way is treating that process of creating software as a problem in the complex domain. We try to release, or at the very least showcase, our software to the customer as often as possible. In other words, we probe. And then we get feedback, we sense, and then we can refine or change our plans, respond. So that's the complex domain. The fourth domain, as you can probably guess, is the chaotic domain. This is more chaotic. So let's imagine for a second that the fire alarm goes off wherever you are. Imagine that the building you're in is on fire. And imagine this isn't a fire drill. Imagine the building really is in fire and consequently you're in danger. So what do you do? In this instance, I would argue your first duty is to get out of danger, get out of the building, get to safety. And only once you're out of danger can you then assess the situation and decide what to do next. This is the chaotic domain. So in the chaotic domain, cause and effect relationships are unclear, and this is the domain of crisis management. Cynefin tells us we need to act and then sense and then respond. Act, in other words, get out of danger or stop the bleeding or put the fire out. Sense, in other words, assess the situation once out of danger and respond, decide what to do next. So examples of the chaotic domain include natural disasters, terrorist attacks, fires, situations where there isn't time to sit and analyze things because it's an emergency, where you need to act quickly to stop things getting any worse. And only once the danger is contained can you then take stock of the situation. In our work as software engineers, we do sometimes have live issues, unplanned outages, and so on. And these are examples of the chaotic domain where, to reiterate, we have to act first before we can sense and then respond. So thinking back to the live release gone wrong at the start of this talk, we released a new version of our service and went to lunch blissfully unaware of the fact that we'd just broken everything and the service was starting to fail requests. So we thought we were in the obvious domain. Now it's clear that we weren't. The question is, what domain were we in? So if you answered chaotic, I'm afraid not, because it was a trick question. Because there's a fifth domain called disorder. And the idea of disorder is, if you don't know what domain you're in, your situation is in, you're in disorder. If you think you know what domain you're in, but you've got it wrong, you're in disorder. So thinking back to our live release gone wrong, my colleagues and I thought we were in the obvious domain because we followed the release process flawlessly, but we weren't. The situation itself was now chaotic, and we didn't know it, and consequently, we were in disorder. This is an extremely dangerous place to be because it makes you handle the situation the wrong way. Here's another example of disorder. Anyone remember the sitcom The IT Crowd? This character here, Moss, has a computer that is literally on fire, and he has incorrectly categorized the situation. The question is, what domain does he think he's in here? I would argue he thinks he's in the complicated domain. He thinks he can send an email to an expert, and that expert will use their expertise to analyze his ongoing fire situation. What domain is the situation really in? It's chaotic. His computer's on fire. He needs to put that computer out, put that fire out, or he needs to get out of the building and get to safety immediately. Sending an email is not a helpful response in a chaotic situation. He needs to do something about that. So if he correctly diagnoses the situation as chaotic, that moves Moss out of disorder and allows him to start dealing with the situation in the correct domain. Here's another example of disorder. Remember the waterfall process that we were made to follow before, many years ago, before we had proven the merits of agile software development. The question is, what domain did the folks who created this process think software development fell into? I would argue, our profession used to think that software development fell into the complicated domain. We just use our expertise, analyze everything, plan everything, and then things will be okay. Unfortunately, it turns out that wasn't quite right. And back then it felt a little different to those of us at the sharp end of it. So here's a question then. Given that developing and releasing software involves unexpected things like changing requirements, getting feedback, and unexpected bugs, what domain do we really think that software development falls into? We've said it a number of times before. The complex domain, the domain where cause and effect aren't obvious, except in retrospect, except when we perform an experiment and see what happens. Because you don't know if your tests will pass until you run them. You don't know what your colleagues will think of the latest code change that you've made until you ask them to review it. You don't know what your customer or the market will make of your software. until you release it. And because of that, we need to build and test and release our software often in order to get feedback and change course in response to that feedback. You might argue that movements in our profession over the past few decades, movements like agile and lean, extreme programming, continuous delivery, DevOps, maybe they represent our profession finally getting it, finally realizing that we had put software development into the wrong kuh-neh-vin domain. Maybe we finally moved out of disorder. One thing that is dangerous about disorder, when we don't know what domain a situation is really in, is that we often proceed according to our personal preference. It's worth asking yourself where you feel most comfortable. You know, maybe your personal preference is for analysis and thinking deeply about a problem. Or maybe you're an adrenaline junkie who loves fighting fires. Maybe you're a stickler for rigidly following a process. Maybe you like to experiment, to try stuff, to move fast and break things. Whatever your preference, it's very helpful to be aware of that preference so you can catch yourself before you find yourself responding to a situation in an unhelpful way. Another thing that's worth thinking about is how situations move between domains. Over time, we tend to see a clockwise drift. So for example, we can move from the chaotic domain to complex if we manage to contain an emergency situation like an unplanned outage. So for example, we get our service running again, serving requests again, we can breathe a momentary sigh of relief as we move into the complex domain. We can move from the complex domain to the complicated domain when we gain so much experience and expertise, we start being able to analyze situations and plan things up front. We can move from complicated to obvious when we learn how to write the task down in the form of a checklist or a script, or maybe we automate the task. So this is all looking rather nice, or is it? Trouble is, if we get complacent, as we did with our live release gone wrong, we can fall from obvious to chaotic. And this is like falling off a cliff. When we did our live release that went wrong, we believed our release process was so well documented and so well automated that it was safe and easy. But then we didn't know about the bug that was going to cause us to fall into the chaotic domain. And so we're told that actually it's not safe to treat important tasks as obvious if there is danger of falling off that cliff. Consequently, we're told that you should move most of your work into complicated and complex. Only move a small amount of work into the obvious domain, because that would make it very vulnerable to this sort of unexpected change. So at Masabi, where I work, we actually do this. When we do a live release, when we release a new version of one of our services into live, we ensure that a developer is present, so someone with the right expertise is present during the release, even if the release is automated. That treats the release as complicated. But we do need to be careful how far we take that. You know, here's a question. Given that releasing our software is really risky, why don't we release our software less often, minimize that risk, release less frequently, put loads of upfront analysis and planning into each release? Well, maybe that's taking us the wrong way. You know, adherents of continuous delivery argue that you should release your software more frequently in order to get more feedback, find more problems, have more opportunities to improve the process. And this treats releasing software as being, once again, a problem in the complex domain where we probe, sense, and respond. So we're pretty much done now. To sum up, kuh-neh-vin is a sense-making framework that defines 4 + 1 domains in which a situation may reside. And it tells us how we can approach problems in each domain. So, you know, the one thing to take away from this is to remember the domains, what they mean, and how to approach them. If you're dealing with a live outage or another emergency situation, that's a problem in the complex domain where we need to act first before we can sense and then respond. And that's very different from following a simple process in the obvious domain, where we sense, categorize, and then respond. And they require different approaches. if you can use your expertise to analyze a situation and formulate a plan, then that's in the complicated domain where we sense, analyze, and then respond. And that's different again to proceeding by trial and error in the complex domain where we probe, then sense and respond. So when you face a situation, again, be aware of your own preferences and instincts, and then try to objectively determine what domain is this situation really in. If you do that, then you'll handle the situation better. And if not, you'll place the situation in the wrong domain and end up in disorder. And that's how kuh-neh-vin can help you to make sense of the situation. If you're still with us, thank you very much for listening. Any questions?
Yeah, thank you, Chris. Sorry.
Thank you. I should add at this point, I don't know how to stop sharing my screen. So if anyone knows how to do that in Zoom.
If there's someone who has some questions, they can raise their hand or put it in the chat.
Stop sharing. Go. I see some stuff in the chat. Dav has pointed out the possibly better definition of the word kuh-neh-vin. Means something like community or locality. Apparently Dave Snowden got fed up of Japanese business people using Japanese words for things and then telling him it's hard to understand if you're not Japanese. So it's sort of a revenge word.
Well, that's what he told me anyway.
Nice.
It is a real word.
Yeah. Yeah, I tell you, I looked it up. Like, my command of the Welsh language is not very good, so it's not a word I'd encountered, and I feel like I'm probably still saying it a bit wrong.
If you remember that there's a hard C at the beginning, as all C's are in Welsh, the rest of it is very recognizable.
Yeah. Well, you've got to remember that F is also pronounced like the English letter V.
Yeah.
If there are no questions, I learned why the letter C is a hard C in Welsh and why the letter C is used like that, although throughout the Welsh language. Apparently,
controversial printing of the Bible.
Yeah, exactly. In the 15th century, the Bible was first printed in the Welsh language, and they didn't have enough pieces that could print the letter K. So a very controversial decision was made.
So I think we used to have a K, just like they do in Cornish, but we lost it because of that episode.
Yeah. Otherwise, kuh-neh-vin would be marginally easier for English speakers to pronounce.
Yeah, I guess so.
I was looking at the Wikipedia. There are a lot of interesting stuff about kuh-neh-vin. It's also the first time that I heard that.
There's a really terrible course on LinkedIn where some project manager guy with a background in manufacturing is discussing Agile with somebody with a software background. So the manufacturing guy is used to making things repeatable. So he's dealing with this most likely in the, what was it called? The simple domain, the one on the bottom right. So he's worried about the reproducibility of very, very simple things, the kind of things you might put on a Gantt chart. Well, Gantt charts were sort of invented for. And he really has a problem with this idea of the other three domains, the ones around the sides. The idea that you might have to explore, you might have to do something to find out how the environment is responding. So he's really not used to this idea that in software you have to sometimes explore a range of options to figure out how things are going to emerge, right? The idea you might have to run a spike and this kind of thing. So it's really interesting watching those two guys, and the manufacturing guy really didn't get that at all. He really just wants a formula that he can perfect, and it's some defined plan up front. I need to have my Gantt, and he really just doesn't get it. But it was really interesting to see the point of view that it wasn't clear to me what it is until you see somebody like that, and then they explain that this is a guy that runs factories.
Yeah. But I suppose, if the factory doesn't work like that, if things aren't repeatable and reproducible, then it's not a very, certainly for certain types of manufacturing, then, the factory is going to go out of business, isn't it?
Yeah, well, it depends what kind of a thing that you're going to make. If the job is, I make millions of bullets, you've made, they're all the same size, they're all made of the same material, they're supposed to weigh the same. The more identical they are, the better. Whereas with software, if you want to make 5 copies of original software, if it costs £1 million, the cost of making one new piece of original software would be £1 million. It's not that 5 copies of new original software is going to be 5 million. It's the reproduction part isn't the expensive part. It's the exploring the problem and figuring out how to resolve the forces.
Yeah, the other thing that really brought this home to me, it was thinking about preferences, thinking about how you instinctively like to handle situations. I think the scary thing for me is I'm really most comfortable, if that's the right word, in a chaotic domain. Like when I went to work for a startup company and everything's kind of on fire all the time, it turns out I was having a great time, which I didn't realize. And when things didn't need to be dealt with as an emergency, when there was actually plenty of time to think about how to respond to this situation and maybe make a plan, that was where I was an awful lot less comfortable.
Where I really see this is, I used to, a really long time ago, when I was less fat, I used to practice Aikido when I was in uni, and it sort of treats fighting as though you're in the obvious domain. Here is a list of recipes, do this, and then your opponent will do that, and then you do this, and then you do that. And it's a waterfall way of thinking about it. I think it's a chaotic activity. And the thing is, if you start to do jujitsu after that, then you realize that you can never jump back into the same stream twice. That the point is, the other person has a brain and they will learn. And as soon as you've acted, they've watched what you've done, and if you fool them once, that's it. You're done. They've learned that, and then there's progress.
Yeah.
Yeah, like that.
So it's
just a comment
true.
about you were saying earlier about the manufacturing thinking they're in the simple or the complicated domain, and I think you could have seen where these guys go wrong, because they become very, very good at producing something, but they just all they can do is lower their prices, and then somebody else comes out and brings it in a different color, or makes it attractive, or in some way adds something that the manufacturer cannot understand why suddenly, is even though it's the same basic thing, customers are willing to pay twice the price for it. And no matter how much they drop their price, they cannot sell their things. Whereas somebody else is selling something that may not even be as well made, but because they've got the marketing and the branding and those kind of softer sides of it right, they're beating them in the market.
There was one thing I saw, the ideas from the Toyota production system have become quite well known in software development sort of in recent years, but there was always this, people used to talk about software engineering, but what they kind of meant was some sort of commodity manufacturing where you're making exactly the same thing, and like you say, all you can do is lower your price. I think it's when people realize that software is actually more like product development, more like the sort of manufacturing where you need to try things and you need to experiment, and you're not going to make the same thing again.
So I think there's a paper called the new product development game.
The new product development game.
Yeah, it's one of the papers that Scrum got inspired from. They were talking about, as you said, companies that are in a competitive corner that realize they need to put an emergency team together because they're in trouble and they know they have to change.
Any more questions, or are we done? Thank you very much.
Put a link to the new product development game in the chat.
Sorry, I just got one more question, which is, are some domains to be avoided? So, for example, the chaotic domain and the complicated domain. Are all domains, or are those actually kind of domains that you want to avoid? That you don't want to be in a situation where it's chaotic, or you don't want to be in a situation where, but it's better to actually to make things complex than complicated.
There is a video with Dave Snowden, who was the guy who originally created the framework along with other folks. He actually says there are situations you want to get into the chaotic domain. These are like a company that wants to come in and disrupt a market. He's talking about this idea of dipping into, basically creating some chaos. So you I don't know if that's a very good example. You imagine that there are certain people in politics over the last 5 years or so who've basically come in and created chaos and profited from it. I think you might argue those are examples of basically profiting from the chaotic domain.
Oh, I see what you mean. And if you want to bring in barriers to entry, then complexity and extra, extra regulation, increasing bureaucracy actually is a good thing because it makes the market more difficult to enter.
Yeah,
I can see that.
Yeah, here's another example that just occurred to me. So it might not be a cool example to come up with, but for example, the COVID crisis over the past year or so, it's been absolutely terrible in almost every respect. But actually, healthcare providers, like for example the NHS in the UK, have been forced to innovate in response to this. You could argue some good ultimately will come out of this once the situation goes a bit more back to normal, once we're actually out of chaos. Maybe for example, people getting telephone consultations with doctors more often, or other innovations in healthcare might stick with us, or other. So
if you're in the chaotic domain, if COVID happens and it dumps you into the chaotic, well, first of all, you're in the middle. What did you call the middle one? The uncertainty
disorder.
Disorder.
Yeah. Sorry. Yeah.
If then you get dumped into, you realize I have no clue what I'm doing. I'm in the act, sense, respond chaotic sort of world. It's a horrible place to be if you have to operate on a national scale with something gigantic like the NHS that moves very, very slow. Like turning an oil tanker around, that sort of thing. It's one thing if you've got a team of 8 developers in a little room and you've got a budget and it's fairly self-contained. If you've got, what is the size of the NHS? The second largest workforce in Europe, something insanely huge.
Yeah, I mean, it's like 1 million or so, isn't it, or more?
You can't get up on a chair and scream, "Stop, everybody, you're going in the wrong direction."
Yeah. But then again, I would argue everyone has been forced to improvise. I know it's been horrible for folks that work in the NHS, like friends and family. I've found the situation very difficult, but actually there, ultimately some good will come out of this horrible situation, I hope.
Well done.
Yeah.
So, thank you, Chris.
Thank you very much, everyone, for coming and sticking with it.
Yeah, see you all next time. I believe there is another one on Friday.
I believe there is, yeah. Maybe see you there.
Yeah, let's see us on Friday on the next talk from LUC. So take care.
See you there.